So hopefully you watched the videos I sent out Monday about intermolecular forces and intramolecular forces. There was one specifically talking about metallic bonding and properties of metallic bonds based on that sea of electrons. So the first thing I'm going to say really quickly is intramolecular forces. It's like the Indianola intranet that we have, INTRA. That's where you're looking at what's going on just among Indianola on the Indianola intranet. If we're talking about intramolecular forces, we're looking at what's going on just inside a sodium and chlorine ion coming together to form salt. What's going on between carbon and oxygen coming together to form carbon dioxide. That's the intramolecular. So intramolecular forces, are ionic bonds, covalent bonds, and metallic bonds. So if we're looking at sodium and chlorine coming together, that's an ionic bond. That's the intramolecular force. So go back and watch those first videos and look at that, especially with the metallic bond. I'm going to take a few seconds here to talk about the intermolecular forces and hopefully gain some understanding on that. So intermolecular forces is going to take place between those substances. So what we have here is we have just monatomic elements. So this could be fluorine, okay? So as fluorine is allowed to be cooled, it's allowed to become closer together, liquid state, continue down to solid state. Like I said, we're just making up an element here. At this point in time, at solid state, you're going to have a stronger intermolecular force. Well, since fluorine's typically a gas, we know that that's not the case. At room temp and standard pressure, it wants to be a gas, so there's not a really strong intermolecular force taking place between those two fluorines coming together. The attraction is between the two different substances. So in this case, we're looking at one atom between another one atom and what's holding them together. Okay, so the first type of intermolecular force we're going to look at is called London dispersion forces, and this is when we do what's called an induced dipole. So this is what I did in class with the pieces of tape. Okay, so when I forced one of those pieces of tape to be opposite. So we bring together these two substances, and notice these negatives shove those negatives to the other side. They repel them, which makes this side slightly positive, that side slightly negative, and you form a little attraction there. Okay, London dispersion forces are forces of attraction. It can happen between all atoms and molecules, but it's definitely going to take place between nonpolar molecules. This is like one of the biggest forces that nonpolar molecules have holding them together, is that induced dipole for a second. These forces are much weaker than any other types of bonding. So if we think that fluorine that I used as an example, that's going to be a nonpolar bond between the fluorine and the other one. So you're going to have London dispersion forces holding them together, which in that case, fluorine's not going to have a strong force. That's why it can be a gas. Now, the London dispersion forces are going to directly relate to the mass. So if we increase the mass, then there's a little bit stronger attraction. So then instead of being a gas, it could be a liquid. And if we increase the mass further, then it could be a solid. Okay, so London dispersion forces between all molecules, but going to be the driving force in a nonpolar setting. Now, if we take a look at hydrochloric acid, we know this to be polar. You've got a bunch of valence electrons out here, and so you're going to have a slightly negative and a slightly positive end. So how do polar molecules come together? Well, they have what's called a permanent dipole. This part is slightly negative, this part's slightly positive, so the positive of the other hydrochloric acid is going to line up with the negative and vice versa. Okay, and it's going to keep going and keep going. So the dipole-dipole interaction is going to take place between polar molecules because there's that permanent dipole. This is stronger than the London dispersion forces. And you can go back and read these things that are on the bottom here once you've watched this video and see that it is a stronger intermolecular force than the London dispersion forces we started off with. Okay? All right, so now let's go to the next one. Hydrogen bonding. Hydrogen bonding is going to take place between hydrogen and fluorine, hydrogen and oxygen, or hydrogen and nitrogen. Okay? Only between hydrogen and fluorine, hydrogen and oxygen, hydrogen and nitrogen. Here's where kids make a big mistake. Between here and here is not a hydrogen bond. Go back to basics. This is a covalent bond, a polar covalent bond, but it's a covalent bond. They're sharing electrons. Okay? So it's not the intramolecular force, that polar covalent bond. It's going to be between one molecule and another. Okay? So as this is going to come up here, we already saw that that was a dipole-dipole, but now it also forms a hydrogen bond because it's taking place between this hydrogen and that fluorine and vice versa on the other fluorine and hydrogen. This is a huge driving force in water, and this is why water has those very unique properties that we talked about the other day, from the surface tension, which what do you see in cohesion and adhesion, and this shows you what happens to those molecules as they're arranged, because the negative is going to line up with a positive, and the positive is going to line up with another negative. Okay. All right. So the hydrogen bonding is going to be the strongest of those intermolecular forces we're looking at. Dipole-dipole would be second, and then London dispersion would be the weakest of the intermolecular forces. Okay, go back and watch the other videos if you need to. Do the worksheet, and like I said, the answer's on the bottom of that worksheet that was attached in Monday's video or Monday's email. And then also I'll send out a link here with this video for some QIA practice stuff for this. Okay, it's just a matter of kind of getting in your head and then recognizing which would make sense. Let me know if you have any questions. Remember, I won't be there on Friday, but if you need anything, please let me know.